So by now we should be familiar with the definition of what it means for a sequence to converge to a real number A. And I've drawn the picture here. Essentially what we're saying is no matter how small we make epsilon, the distance that you're allowed to move up from A and down from A, there's always a way to cut your tail such that the entire tail contains values that are inside that epsilon range. So that's what our capital N stands for. It's the place we chop our tail. Now, what does it mean for AN to not converge to A? So if you hand me a real number A, how would I prove that AN doesn't converge to A? And as you guessed it, the notation, as usual, if you want to say not something, you just put a slash through the arrow to say it does not converge to A. So I would pause your video, see if you can write out the negation of the definition, and then see if you can get yourself a picture that shows what's going on too. So I've written out the precise definition. If I just use negation rules, I should get that there exists an epsilon greater than 0 such that for all capital N, I can find a little n greater than or equal to capital N that is greater than or equal to epsilon away from A. So at a high level, when AN converges to A, no matter what epsilon I pick, I should be able to find an n such that all values are in the band. And so the negation of that should be, there's got to be some epsilon band such that no matter where I chop the tail, there's always an outlier that is not inside the band. So the key here is to recognize this is saying there exists an epsilon. It may not be that all epsilon have outliers. If you have an oscillating sequence, an epsilon that spans the width of the oscillation wouldn't have outliers. But the way I've drawn my graph, the specific epsilon I've picked has been small enough such that no matter where I try to say my tail is, there's always an outlier. So let's say I try to pick capital N to be here, and I'll say this is my first attempt. Well, then I could say this guy right here is an outlier. It's a guy in the tail that's not in the band. And so then I could say, well, go further, try to chop your tail here. But then notice there's an outlier here. And then I could try to say, well, keep going. Pick this n value. Again, there's another outlier. So no matter what we pick, there's always going to be an outlier past that tail. So no matter where we chop the tail, that's like saying for all capital N in the natural numbers, which is our choice of tail. So no matter where we chop the tail, there is an outlier outside the epsilon band that's in the tail. This right here is our outlier. We're saying there is an index that's too far away. So we've given the definition of what it means for a sequence AN to not converge to a specific real number A. We need to go a step further and ask the question, what does it mean for AN to diverge? Just because AN doesn't converge to 5 doesn't mean it couldn't converge to 7, for example. So we need a precise definition here. In particular, we should be able to show that for all choices of A, so for any limit that we try to pick in R, AN does not converge to A. So no real number is the limit of our sequence. And if you can demonstrate that, then you can say that A sub n diverges. So I want to take a look at an example just to get us used to proving that a sub n doesn't converge to a specific value. So we have this example of our prototypical oscillating sequence. It's the sequence -1 to the n. And we're going to prove that an doesn't converge to 1, for example. I would encourage you to draw yourself a picture. What I would do is write out the definition of what it means for your sequence not to converge to 1. Draw the picture specific to the sequence -1 to the n, and see if you can start making progress on how you would demonstrate that no matter where you chop the tail, there's always an outlier. So pause your video and try that. So if I customize the definition of an not converging to a specifically to my problem, my a value in this problem is 1. So I'm going to say I'm looking for, I want to show there exists an epsilon greater than 0 such that for all n there's a little n greater than or equal to capital N, such that the distance between a term in my sequence and the limit that I'm not approaching 1 should be too far. It should be greater than or equal to epsilon. And so I've drawn a picture of my sequence down here, and we're going to be putting an epsilon band around the number 1, because 1 is our value that we're supposedly not converging to, and we need to find a thin enough epsilon band such that when we do that, there's always going to be an outlier in the tail, no matter where we chop our tail. So one question you might ask yourself is, which values are valid choices, or are a valid choice for epsilon? Because this is an existence statement, which means we just have to find one epsilon, but if one epsilon works, any epsilon smaller than that will also work. So how big can epsilon be? I would pause your video and ask yourself, how large can we allow epsilon to be such that we'll still have outliers? If you take a look here on how I've drawn my epsilon band, what we end up getting, all of our outliers, the points that aren't in the band, are these numbers that evaluate to -1. So they're all the odd indexed values in my sequence. Now, if I'm going to guarantee that I have outliers, epsilon cannot include those outliers. So my epsilon band cannot include the y value of -1, since those are my outliers. As soon as I go wider than that, I don't have any candidates for showing that there's no place to chop the tail, because the whole sequence will be included in my band. So I'm allowed to use any epsilon such that 0 is less than epsilon, which is less than or equal to 2, will work. Because notice that what I've done is I've measured the distance between 1 and -1. This is a distance of 2 wide. And the epsilon band does not include its limits, the edges of the band. Remember, it's a dashed line. So if epsilon were 2, my band would go right up to -1, but -1 would be the boundary and it wouldn't be included, which means all of those points would be just on the edge of my band at -1, and those would still be outliers. So what I need to do here, so now I know I can pick any epsilon I want. I need to come up with the argument how no matter what capital N I pick, I can always find a little n bigger than it that will give me an outlier. So but really I'm just looking for a subscript that's odd. I'm going to go ahead and write out my proof here. So proof. To write up my proof, I need to follow the structure of the definition. I need to show there exists an epsilon. So my first step is to let epsilon equal some value. Now for me, we said we can pick any number that's positive but less than or equal to 2. So I'm going to pick epsilon to be a half just for fun. You can pick any value you want. So any epsilon such that 0 is less than epsilon, which is less than or equal to 2 here. Now, if you're writing your proof, you don't need to tell me that, but this is just from a notes perspective. As you're trying to make your decisions, it might be helpful to have it noted how we were able to pick an epsilon that works to begin with. So let epsilon equal a half. The next step, so we've checked that piece off. The next step is now to introduce an arbitrary n, capital N. So we're going to choose an arbitrary capital N, and then we need to argue that there exists a little n greater than it. So we know by the Archimedean property, part 1, given any real number, there has to be a natural number that's bigger than it. There exists a little n greater than or equal to capital N. Now, either that little n that we've found is odd, in which case it's the outlier we're looking for because it evaluates to -1 in my sequence, or maybe I could use little n plus 1. If you want to be really clever, we could say that 2n plus 1 is greater than or equal to capital N. And if I look at a sub 2n plus 1 minus 1, that's going to give me -1 to the 2n plus 1 minus 1, which is 2. And that is strictly greater than a half, which is my epsilon value. So here I'm actually using my outlier to be the subscript 2n plus 1. That's just to be clever, to guarantee that the number I'm working with is definitely odd. I could have gone through an argument to say, pick your little n, at this stage right here. If n is odd, a sub n minus 1 is 2, which is bigger than epsilon. Otherwise, a sub n plus 1 minus 1 is 2. So that's it for that proof. And then what you would ask yourself here is, have we proven an equals -1 to the n diverges? Well, and the answer here is no. We've only shown it doesn't converge to 1. We would need to show that it doesn't converge to L for any choice of our limit. Or A. Would need to show for all A in R, AN does not converge to A. So that's it for divergence.